Alrighty, folks, we're going to begin our next unit. Right, this unit is going to focus on sound production, how we hear sound, human perception of sound, the way that sound is going to operate, the speed of sound. Right, everything here based on sound. Right, what is it? How does it work? So, in order to first start talking about sound, right, you've got to be able to determine how you can actually make sound. Right, and sound by nature is a longitudinal wave, which means there has to be an area of high density and an area of low density. Right, going back, so we're going to have our compression area and our rarefaction area as sound moves through some medium. Because sound is a longitudinal wave, that means it is a mechanical wave, and that also means that it does require a medium to travel through. So it needs a solid, a liquid, a gas, right? It cannot travel through a vacuum, right? It needs some substance with which to travel through. Now, when a vibration is created, right? So if we look at the diagram on the slide here, right, we have a tuning fork, right? So you strike a tuning fork, and the ends on that fork vibrate back and forth, right? So if we watch here, right, at some point that tuning fork will press outward, and then as it presses outward, it's going to reach some maximum distance, then it's going to retract back inward. So when it's pressed outward, right, notice the high density air is on the outside. Then when it retracts, then it's going to be left with a lower density region. Similar example on this, when you go underwater and you try to clap your hands, right? Picture you're trying to clap your hands. So when you bring your hands together, really you're forcing that water to be together, which means behind your hands, you're actually leaving a slightly lower density of water, right? You have more water particles between your hands than you do directly to the outside, right? Similar idea here. Again, that high density area, right, is going to be our compression, and our low density area is going to be our rarefaction. So you need some sort of vibration, and you can even test this with yourself when you speak. If you feel your vocal cords when you talk, right, you're going to feel them vibrate, and that vibrational pattern that they create is then going to go out of your mouth into the air, and it's going to that same vibration that you get on your vocal cords. That vibrational pattern is going to be matched by the actual air that is then going to have the sound travel through it, right? So that vibration causes the air to vibrate, and that vibration continues to move through the air until it gets to somewhere that we can hear it. Now, as we use our tuning fork here, right, just keeping with that tuning fork example, right, we can actually translate a longitudinal wave into a transverse wave. Right? Because typically when we see waves, we see transverse waves, right? That's your sine cosine pattern. So if you look at that tuning fork picture here, right, we see the high density represented in the darker blue, the low density represented in the lighter blue to white, right? White is going to be the lowest density, that dark blue is going to be the highest. So how we translate longitudinal waves to transverse waves is the high density becomes the crest, the low density rarefaction becomes the trough, right? And everything else just kind of falls in between, right? So every crest is associated with a compression, every trough is associated with a rarefaction. And we can actually see that in this simulation here, right? So if we take a look at the simulation, notice the longitudinal wave on the left being translated to the transverse wave to the right. And one important piece to notice about this longitudinal wave, as specifically as you watch this part in red, the longitudinal wave moves based on contact with particles, right? The particles themselves move within a very, very small window. They don't move with the entire wave, right? They like to stay relatively in place, right? So here we see a compression and then a rarefaction, and then a compression, right? So you can see how the slow transition yields that transverse wave. And again, our particles are in motion, but they don't move completely with the wave itself, right? The wave is able to pass through and give that energy to more and more particles as it moves. But again, here we have a compression with a crest, and there we had a rarefaction with a trough. All right, so again, just to show you guys that quick demo there. Now, when we categorize sound, right? So humans, right, we like to put things into these nice little categories, right? We like to refine things and know, okay, what fits here, what fits there, what fits, what are our, how can we compartmentalize things, right? How can we organize things? So we do the same for sound. We have 3 ways that we categorize sound: infrasonic, audible, and ultrasonic. For an infrasonic wave, right? Infra meaning under, right? Those are the waves that we cannot hear, right? So 0 to 20 hertz, we cannot hear those sounds. 0 hertz makes sense, right? That would mean that nothing is vibrating, right? 20 hertz, that would be very, very, very low frequency there, right? So we can't hear those sounds, right? That's below our range of hearing. However, when earthquakes, right, start to happen, earthquakes will rumble, right, and they'll actually produce sound that we cannot hear, right? So those sound waves are at a frequency lower than our range of hearing. Elephants you see on there, right? Elephants are actually able to communicate in this range, right? So some animals, right, elephants specifically, will have vocalizations that are in a range that we cannot hear, right? So they can be communicating with each other with a human standing right next to them, and we won't be able to understand it. We won't be able to hear it, right? Because it's below what our ears can pick up. The next category is the audible waves, right? And the audible waves, this makes sense because this is what we can hear, right? So we can hear on average 20 hertz on the low end, 20,000 hertz on the high end. And again, that's the absolute extremes, right? If you can hear 20 hertz, you're in the minority. If you can hear up to 20,000 hertz, you're again in the minority, right? Most people, right, especially right younger ears, right, are going to be anywhere from 60 to 100 hertz on the low end on average, up to 19,000 hertz on the high end. As you age, right, or as your eardrums, get worse, quite frankly, right, that range begins to shrink, right? So you start thinking about, people that struggle to hear. It's because they're missing the low end and the high end of that human range. The other thing to look at here too, right, is the difference from, let's say 50 to 60 hertz, right? A 10 hertz difference on the low frequency end is huge. The difference of 500 to 510 hertz, not as huge. The difference from 1000 to 1010 hertz, even smaller. From 10,000 to 10,010 hertz, really small, right? So as we really start increasing that frequency, our ears don't pick up the differences as well, right? As you go further down that scale to the lower frequencies, our ears can pick up differences in that frequency, so in the pitch of the sound, much, much, much more easily as we go towards low frequencies. As we get towards high frequencies, our ears can't pick up those differences as well. Ultrasonic is the last type here, right? So anything above 20,000 hertz. Ultra meaning over, right? We can't hear anything above 20,000 hertz. We can still feel it. So if it's there, and if it's powerful enough, we can feel it. We just can't hear it. And I guess the same thing does go for the infrasonic, right? Did not mention that. If you have a sound that's under 20 hertz and it's powerful enough and it's an intense enough sound, you can feel it, but you don't hear it. So ultrasound, for example, right? Medical, we use this medically, right? Ultrasound, so being able to see images within the human body, right? So we'll use sound right there. Also thinking about, like depth finders, right? Fish finders, right? They rely on sound to be able to do that. Dogs, right? Dogs are on here because they can hear in this range. So if anybody has trained a dog using a dog whistle, or if you have, really that's the big one, right? Using a dog whistle. Dog whistles, when you blow them, they play a tone that is above 20,000 hertz. So it's a very, very, very high frequency, which humans can't hear. The dogs can. The dogs don't like it, right? It's a very uncomfortable tone, so it makes them run back, right? That's part of training for a dog. Frequency and amplitude, right? Again, just kind of how we perceive frequency and amplitude in terms of the sound that is actually produced. So frequency, again, being hertz, right? So a high frequency means that we have a lot of cycles per second. A low frequency means we have very few cycles per second. So frequency, we relate to the pitch of a sound. So something that's a high pitch, so if you want to think about, characters, so a Mickey Mouse, for example. Mickey Mouse, right? He'll talk in this really high pitched voice, right? So that high pitch is a high frequency. Or sometimes you get people that talk with a really, really, really low voice. That really low voice is a low frequency, so it's a low pitch, versus the high frequency, which is a high pitch, right? So that high frequency we associate with high pitch, low frequency we associate with a low pitch. Amplitude, on the other hand, right? Amplitude is going to deal with the amount of energy that that wave has. So the amplitude is dependent on the volume. When you change the volume on any sound producing device, right? Whether it's the radio in your car, whether it's a stereo in your house, whether it's your earbuds, right? Whatever it may be, when you turn the volume up, you're really increasing the energy of the wave, which increases the amplitude of that wave. Right? So amplitude is dependent on how loud or soft that wave is. Frequency is dependent on the pitch. Just because it has a high energy does not mean you're changing the pitch. Picture when a good song comes on and you turn up the volume, the pitch of the person doesn't change. The volume of that person changes. Right, so what this diagram is showing us here, right, and how it all relates back to human hearing, relates the intensity on the left-hand side to the frequency on the bottom. So note the frequency range from 20 to 20,000. And again, note the bottom here, right? We go 20, 50, 100, 200, 500,000. I mean, our windows really expand as we get higher and higher frequencies because our ears aren't as perceptive to changes of higher frequencies compared to lower frequencies. Right, we get this threshold of hearing, this kind of U shape along the bottom. That pertains to the intensity of the wave and the frequency of the wave. Right, so just because I say that, yep, you're right, you can hear something that's at 100 hertz, well, if the sound isn't powerful enough, if it doesn't have enough intensity, it doesn't matter if it's in the human hearing range or not, you're not going to be able to hear it. Right, so part of that range also depends on how strong that sound is. And notice where you need the lowest amount of intensity is on average between 500 and about 7,500 hertz. Right, that range, right, we are really, really, really good at, right? Specifically between 2 and 5,000, even more so. And as we get towards our threshold of hearing in terms of the frequencies that we can observe, note that those intensities have to be really, really, really strong to be able to hear that sound. Right, and then we have this thing at the top, this threshold of pain. Right, that threshold of pain, if you're within the range of human hearing and the intensity is high enough, it will cause you physical discomfort and physical pain in order to hear that sound. What this is also showing us is the speech versus the music region, right, versus all other sounds that we'll hear. Right, our speech region, on average, 100 to about 8,000 hertz. And our intensity doesn't change very much. The music region is a little bit more, right? Because when we sing or when you produce music with an instrument, you're not going to want to produce something that's going to hurt. But instruments have a larger range of frequencies which they'll play with, and also you can control the intensity of the sound more so versus when you're just talking. And that's the same thing for singing too. When people sing, right, they can change the frequency of their voice more so than when they're just talking. So that's what we have here for just initial sound, right? What is it? How do we make it? How do we hear it? How do we categorize it, right? And what does it all end up meaning in terms of our interpretation of sound?